Okay, we're going to finish up the last little bit of this chapter, like I said, and then afterwards we'll talk about the lab report. Comes back, there we go. And then we'll talk about the finals, and then we'll stop talking and we'll just leave, I suppose, at that point. All right, so we've been talking about binding energy per nucleon, and what we did a couple examples. Let's do this last one here. Again, give me some information. Once again, our proton is 1.007825. Our neutron is 1.008665. And why don't we do it for both types of units? Let's do joules per nucleon. And we'll do mega electron volts per nucleon as well. All right, so take a few moments there, work it out, see what you come up with. Should be 26 iron, I believe. Yeah. Okay, let's take a look again. You do have two options as to how to do this, as we talked about earlier. You can use E equals MC squared. You could also use, again, those kind of conversions that we saw as well that are based off of it. Like 1 AMU is 931.5 mega electron volts. And again, they both should give you pretty much the same answer, maybe slightly different if you do a little bit different rounding. You also could use, obviously, mega electron volt is our 1.602 times 10 to the minus 13 joules. And again, whichever way we want to go. Now, the first thing we need to figure out, obviously, is the number of neutrons. So our neutrons, again, going to take our mass number 56 minus our atomic number 26 should give us 30. That will then allow us really to calculate the mass defect. And that's going to be, we'll go 30 times our 1.008665 for our neutrons. We'll add it to our protons, which was the atomic number 26, times the mass of the atomic number of a proton, 7825 AMU. We're then going to subtract that from the atomic mass of this isotope, which is 55.93494 AMU. Yeah. Did it stop right? Yeah, I woke up. There you go. See, technology not good today. I don't know. Let's see. All right. So grab a calculator here. 30 times 1.008665 plus 26 times 1.007825 minus 55.93494. That's going to give us a mass defect, which again is that mass is going to be kind of converted into energy of about 0.528 AMU. Again, like I said, you can use that into here, multiply it by the speed of light and divide by Avogadro's number to the 26 to convert it into joules. Or again, you could just kind of use these conversions if you want and not even worry about it. So we'll go 0.52846 AMU. And we'll go 1 AMU is 931.5 mega electron volts. That's going to get us here about 492.26 mega electron volts. We do want it per nucleon, so we're going to divide by the atomic number, which is the number of nucleons, which is our protons and neutrons. And we'll go 56 on that. And that's going to get us basically an 8.790 mega electron volts per nucleon in that case. We also wanted joules in this case. So since I did go this route, actually, you know, I'll show you with the Einstein equation in case you want to go that route. But obviously, you could use this one here to get it to joules, or you can go into here again just to show you this move here. And again, times it by the speed of light. Obviously, if you went this way, you probably wouldn't have done this one first. And we will end up with 0.52846 times 3 to the 8 squared. That's going to give us 4.756 times 10 to the 16. Again, this is AMU meters squared second squared. We're going to turn this into a joule by dividing by that Avogadro's number to the 26th. And again, if we take our 6.022 times 10 to the 26 AMU per kilogram, that will do it for us. And we'll get something like 7.898 times 10 to the minus 11 joules divided by our 56 for our nucleon will get us here about 1.41 times 10 to the minus 12 joules per nucleon, which again, you should get if you use that conversion going that way. Again, slightly different maybe with the rounding, but you should be pretty much the same number. Any questions on that there? Now, if you remember last time in the lecture, we did two other ones. We did the fluorine, I think, and the carbon. And I think the fluorine came out to 7 point something mega electron volts. I think the carbon came out to 6 point something mega electron volts per nucleon. And here we see actually iron at 8.7 is based on binding energy the most stable. And if you remember from that graph that we saw about this, there it is right there, iron 56 right up on top. It is again kind of the most stable there based on binding energy per nucleon. And that's the one we just did there. And as you can see, kind of at the top there of stability based on binding energy per nucleon. Any questions on how to calculate that? Again, also another measure of stability. All right, to finish this up here, we'll talk a little about nuclear transmutation. Nuclear transmutation is really this process, for example, of sort of shooting particles at nucleuses. When they do that, they're not very happy about that, and they become a little unstable, and they will make new nucleuses. You could do that with a particle accelerator. It's got a magnetic field and electrical field. Basically, get the particle moving really fast, and you shoot it at your target as obviously it has a charge, so you can take advantage of magnetic and electrical fields to do so. That is like all those guys on the bottom of the periodic table, the very last one, uranium, where they make up all those elements. No, I'm just kidding. All those man-made elements like we have our Einsteinium, our Californium, our Berkeleyium, our Nobelium. Again, you can see they're all, for the most part, produced by sort of this process where you shoot a particle out of a stable nucleus, it becomes unstable and produces, some of these man-made sort of elements along the way. This is also a process that could happen with fission. So fission can be spontaneous, as we talked about earlier, but you could also do this as well. So if you take a stable isotope of uranium and you shoot a neutron at it, it then becomes a bowling pin and unstable, and it splits off into two new nucleuses. Like I said before, it will usually produce a lot of neutrons as a result of this fission reaction. And most importantly, as you can see here, it will also produce a lot of energy will be produced as well. And again, that is essentially kind of the reaction that is used in a fission reaction, like I said earlier, in like things like nuclear power plants, they use fission reactions. And again, it just generates a lot of energy through this reaction. And it also is almost self-sustaining as well, because as we will see shortly, neutrons kicks it off and you make more neutrons, which allows this reaction to potentially continue on pretty smoothly and continuing on. So as you can see there, you get 2 times 10 to the 13 joules of energy per uranium-235 that is used in a fission reaction. And if you compare that to a combustion of a ton of coal, you only get 5 times 10 to the 7 joules. The comparison there is in a traditional power plant, they burn coal to make power. And in a nuclear power plant, they use a fission reaction to do that. And you can see a lot more energy, obviously, in the nuclear reaction. Now, when you go through a fission reaction, you do not always generate the same two guys. So you don't always get the same two sort of products that come out. You do definitely get the neutrons and the energy always, but you don't always produce the same ones. This chart just kind of shows you some common mass numbers of what is produced, but you can produce different things always. So you may not always get the same sort of products as a result of that. And as I mentioned before, this reaction can continue on, and this is what is sometimes referred to as a nuclear chain reaction. And a nuclear chain reaction is basically a self-sustaining reaction of a fission reaction because, again, as I mentioned before, basically the neutron kicks it off, and you can see you're just forming more neutrons, which could just go back and hit some new ones and continue to grow exponentially as you continue to do that. Every time it does so, you're obviously making a lot of energy, a lot of radioactive products along the way as you do that. The minimum amount of mass that's required to keep this reaction just going and going and going, that is what is known as the critical mass. So the critical mass of uranium is what is needed to basically just leave this thing just keep going and growing exponentially as well. So if you do have a critical mass of it, you will get this growth exponentially. You will create all these radioactive products along the way and release a ton of energy as it continues on. How do we kind of keep it a little bit under control? You use sort of a non-critical mass of uranium, for example, and that allows this reaction not to just keep kind of growing and growing because there's just not enough uranium to do that. Sort of a traditional sort of atomic bomb here. They have a subcritical mass of uranium there, and on the other end, the wedge that's going to fit in there separated. So when this hits, it explodes, makes the wedge go in, completes it. And now you have a lot of energy, and you have now a critical mass of uranium, which will obviously kick off this reaction here, creating a lot of energy and obviously a lot of radioactive sort of products that are bad in itself. Now, why does that maybe not happen in sort of a nuclear power plant? It's because of a couple of things that are there. Basically, all power plants, for the most part, kind of work similar. They usually have some water, kind of heat the water up, and the steam that is made is used to go out to the turbines, to the generators, and you get electricity. And because it's steam, if you cool it back down, you get the water back, and it's a nice little cycle that happens. The difference between sort of traditional power plants is they burn coal there in a combustion reaction to heat the water. In a nuclear reaction or a nuclear power plant, they use a fission reaction to heat the water. As you can see here, this is a cross section of a nuclear power plant. They usually have very big domes around them. Our closest, I think, is San Onofre. I don't think they work anymore, but that's where they were located. They're off the 5 freeway. Maybe seen the two big domes. They usually are near a big body of water, so they could kind of recycle those type of steam and kind of keep that whole thing generating. So usually in that type of reactor, there's a couple of things. There are what are known as fuel rods. And fuel rods are like eraser-sized pellets of uranium, basically. And that obviously is what powers sort of the reaction and kicks it off. And that heat that's coming off from that fission reaction, kind of in this insulated water guy, goes through the bigger water, kind of the non-radioactive part, if you will. And obviously that's going to generate a lot of heat coming off of this. It's going to heat this water. It's going to create this steam that's going to go out, obviously, to make power. And obviously it can be condensed back through coming this way as well. What keeps this under control is a couple of things. They use a non-critical amount, obviously, of uranium. And they also have other things in there which are known as control rods. And control rods are rods that are dipped in things like cadmium. And cadmium's a really good neutron absorber. And that's pretty important in this type of reaction since It is the neutron that kicks it off, and it is the neutrons that come back around and keep this reaction going. So having these control rods in there, they essentially kind of grab out a lot of the excess neutrons that are performed, and that keeps the reaction not to go critical there and keeps it under a control. Unless, of course, you take out too many of the control rods, then you have a problem and this reaction kind of goes a little bit out of control. Any questions on that there? No. Obviously, there is good and bad for both. Coal fire is not radioactive in a sense, but obviously it does create a lot of pollutants. Also, to get the coal, it also involves probably stripping down some land to do kind of mine for all that kind of stuff. Obviously, in nuclear fission, you have a lot of nuclear waste, obviously, right? And for a lot of years, that was a problem because nobody wanted the waste to go through their neighborhood to be disposed of. So, for a lot of years, people in terms of nuclear power plants, they would actually just keep it all on site because they couldn't really send it anywhere. A lot of years ago, and at this point, they opened up a place in Nevada, I think, where they now have sent a lot of that stuff. That's how they get the neon lights to stay glowing over there on the strip, right? But they've moved a lot of that stuff there. A lot of the nuclear power plants are decommissioned, a lot of them, because it's too much money to upgrade them and stuff like that. So, like I said, up until a number of years ago, they had one in San Onofre, I think that was still working. I think now they're both kind of down and not working anymore. Part of the also side effect of a fission reaction is you get a lot of what is sometimes referred to as spent fuel. And spent fuel is really the radioactive products that are made as a result of these fission reactions. The problem with obviously the waste, which has a lot of the spent fuel in it, is as you look in terms of storage time and years, it takes a lot of years to keep this stuff around before it is safe. And that creates a lot of things, like I just said, like where do you put it, who's in charge of it, right? And what do you put it in and stuff like that. So, and obviously a lot of the spent fuel in these type of fission reactions could be used for things that are not friendly as well. Um, the next thing we're going to talk about is fusion, and fusion is a little different than fission. So fission, we kind of break something apart into two nucleuses. In fusion, we put two smaller guys together to kind of make a larger sort of atom. The result of that is it is usually done at really, really hot temperatures and high temperatures, like you're vacationing on the sun type temperatures, super hot temperatures. That's why all those movies are they're always interested in the guy that could do cold fusion, right? Rather than right, they're always trying to find that scientist in those spy type movies. But it's usually done at very, very obviously high temperatures. Lastly, here, obviously, radioisotopes can be used in medicine, as we talked about earlier. You definitely would want a smaller half-life if you're using something for medicine. They can be used to treat all kinds of things. They used to implant radioactive sort of seeds in tumors to shrink them. They also could do something like sodium here as a blood tracer. We have iodine for brain imaging. One of the nice things about, I guess, sort of radioactive isotopes is in the body, they do perform the same sort of functions as sort of the non-radioactive version. So if you are interested in what's happening, you could use something like this and it will sort of highlight that. Obviously, you can scan for the radioactivity and get sort of a picture of what's happening. Um, we oftentimes will use this in sort of research labs as well. In the sense that, you know, if you're working with a protein that involves copper or something like that, you could use a radioactive version of copper and you could do like protein purification and figure out where all the copper ended up all through the process by just following the radioactivity. And that's a very common sort of use of some of these isotopes here. And as you can see here, some imaging, technetium 99 there, giving that in your bone scan there as well. If you ever use radioactive material, you'd be familiar usually with this guy here. This is a Geiger counter, and a Geiger counter is a little wand thing. You go around, it beeps, beep, 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 right? If you have a lot of radiation, hopefully not too much. You point it at yourself. Hopefully it doesn't beep too much and that stuff. In addition to, as I mentioned before, a lot of times you wear a ring if you're really working with it, and also a badge on your lab coat. And then you're like a lot of people that just put their lab coat on the chair right next to the radioactivity, go to lunch and never really use it. And then they go develop their thing and go, you really should like get out of the lab for a while because your badge has been sitting like right next to the radioactivity nonstop for 40 days. So you want to really be careful. So usually you'll use this to, um, when you're cleaning up and when you're doing radioactivity or using it, please check the counters afterwards, check your shoes so you don't walk on something and take it home with you. If I hold a Geiger counter up, will it make a noise? It will. There's background radiation, yeah. So those hopefully should make a loud noise, but it should make some type of noise. And there is background radiation, as we can see here. We do get some background radiation from some different sources, cosmic rays, X-rays, air travel in case you live near nuclear waste, I suppose, or weapons testing, in case you bought that stuff. So there's two types of sort of things we look at. There's a RAD, which is a radiation absorbed dose, and the REM, which is sort of the human factor of it. And that's basically just a RAD by multiplied by a conversion factor here. As we saw, I think at the beginning of the chapter, depending on the type of emission that's happening, they do penetrate a lot further in the skin and into the body, obviously into lead. And as we saw there, gamma and beta particles do travel a lot farther in, so you can be absorbed a lot less of that. You can hit a lot more of the alpha since it doesn't travel as much into there in terms of that. So that's why that number is a lot larger. Those are strawberries. Good talk. I like it.